continuing on in section 3.9 on matrix norms. Okay, we'll pick up with an idea we've seen before of the inner product of two matrices. Suppose matrix A and B have the same dimensions. Let the columns of matrix A be A1 through A sub m, columns of matrix B be B1 through B sub m. We've defined in the past the inner product of two matrices as the sum from j equals 1 to m of A sub j transpose B sub j, treated as a matrix product here. So we have a sum of matrix products. And since the subscripted lowercase a's and b's represent columns of these matrices, then A sub j transpose, that's the transpose of the jth column of matrix A, as a matrix product times the jth column of B. So it's really just an inner product. So we had defined these inner products of two matrices as the sums of the inner products of their corresponding columns. If we denote the entries of the matrices as with double subscripts, matrix A is lowercase a sub ij, similarly for matrix B, then we get for this inner product, when we expand out the inner products of the columns, we get a double sum over products of all corresponding entries of the matrices. So if we take an inner product of a matrix A with itself, then we get the A sub ij times A sub ij itself. We get a double sum over all rows and all columns, A sub ij squared. It's the sum of the squares of all the entries in that matrix A. And that's exactly what we would get for the Frobenius norm squared. We've also seen in the past that the inner product of two matrices A and B can also be computed as the trace of the transpose of the first times the second. So we could express the Frobenius norm itself as, say, the square root of the inner product. We could also express it, since the inner product of a matrix with itself can be expressed as a trace, as the square root of the trace of A transpose times A. Now, whenever we express a norm as a square root of an inner product, that's called a norm induced by that inner product. So what we're getting then is the Frobenius norm is the norm induced by the matrix inner product. If we were to transpose matrix A, it's a quick little observation, the Frobenius norm of A transpose equals the Frobenius norm of A. Well, if I view that Frobenius norm as the square root of this double sum here, sure, the entries of A sub ij, the entries A sub ij of matrix A are precisely the same entries of A transpose. We'd get some rearranging on the sums, arguably, but certainly when I transpose a matrix, it keeps the same entries, and the Frobenius norm is determined by summing the squares of the entries. So A transpose and A have the same Frobenius norm. In fact, more generally, first theorem of this video, if square matrices A and B are orthogonally similar, the claim is the Frobenius norm of A equals the Frobenius norm of B, and let's go through the proof of that. Okay, orthogonally similar matrices means there exists an orthogonal matrix Q such that A equals Q transpose B Q. Okay, so for the Frobenius norm of A, it's convenient to express it in terms of the trace of that matrix product, as we just observed. We've got matrix A represented as Q transpose BQ, so we'll replace A with that. We'll replace A transpose with the transpose of that. Write down these matrices transposed in the opposite order. That'll give us a Q transpose, a B transpose, and a Q transpose transpose, or just a Q. Given the definition, well, given the representation of matrix A. When we have orthogonal matrices, you know matrix times its transpose is the identity. When we have an orthogonal matrix, its inverse is its transpose. So we can replace the Q transpose with an identity. I'd like like to do that again, but I've got the Q transpose and the Q's in the wrong place. We state in one of the exercises from several sections back that the trace of C times D equals a trace of D times C when these are square matrices. Here, if we'll take matrix C to be the left-hand two matrices multiplied together, and we'll take matrix D to be the right-hand two matrices multiplied together, then I can interchange BQ and Q transpose B transpose, putting the BQ first and those transpose matrices second, according to that result about traces. And then we got the Q and the Q transpose together again, saying that's an identity and ignoring it, giving us the trace of B transpose. The trace of a product is the trace of the product in the opposite order. So we can rewrite this trace of B transpose as the trace of B transpose B, applying that exercise again. And that's exactly what we had as a Frobenius norm. So we get the Frobenius norm of A equals the Frobenius norm of B. And let's return to the notes. When A and B are orthogonally similar. Now, we can also look at the Frobenius norm in terms of spectral decompositions. Since the Frobenius norm is induced by the matrix inner product, and the spectral decomposition of A can be written in this form, where we had these, this came from orthogonal matrices. Remember, a spectral decomposition allowed us to introduce these spectral projectors, and they satisfied an orthonormality condition. This is stated in Theorem 3.8.17, the establishing of these claims. And we had the d sub i's, the coefficients, written in terms of inner products. So we can say that the Frobenius norm squared equals the sum from I equals 1 to R of these d sub i's squared. Whenever you have a representation of a matrix or a vector in terms of an orthonormal basis, and that's what we're getting here. These things form an orthonormal basis. These outer products, U sub I with V sub I, outer product is what we have there. These are actually matrices, and the inner products of those matrices are shown to be 1 and 0, respectively, for I and J. J equals I, we get out 1. I and J are different, we get out 0. There's the orthonormality condition on those matrices, those outer products. And whenever we have a matrix represented in terms of an orthonormal basis, you can always calculate, this is Parseval's identity, you can always calculate norms by summing up squares of coefficients and taking a square root. So the Frobenius norm can be related to the singular values of matrix A as given there. We showed in Theorem 2.1.10 that all vector norms in a finite dimensional vector space are equivalent. Let's look at the definition of equivalent norm. It's been a while. Definition of equivalent norm was exactly what's given here from some notes from section 2.1. Two norms, an A norm and a B norm, are said to be equivalent if there's positive constants, R and S, such that we get the A norm of X sandwiched between the B norm of X and scalar multiple R times the B norm of X and scalar multiple S times the B norm of X, where we're allowing X to range over the vector space on which these are norms. And again, the R and the S are fixed. So we have some constant multiple of the B norm of X that's always less than or equal to the A norm of X, which is always less than or equal to some constant S multiple of the B norm. So there's a sandwiching type thing here. Probably you were given this as an exercise to show it actually is an equivalence relation. But that's what we meant when we said that vector norms are equivalent. We could treat matrices as if they were vectors. That's kind of what's done when we look at the Frobenius norm. In exercise 3.28, it's to be shown that any two matrix norms induced by vector norms are equivalent. Okay, that should be a fairly standard manipulation of the definition of equivalent, the fact that we know that vector norms are equivalent by that result. We just looked by that theorem 2.1.10 with the definition we just looked at. Gentle goes further than that and states that all matrix norms are equivalent, not just those induced by vector norms, which makes perfect sense. As vector spaces, I can treat the vector space of all n by m, the way Gentle normally does it. I can express the collection of all n by m matrices as a vector space. In fact, when we defined the inner product on matrices, it was quite similar to the way, well, it was virtually identical to the way we define inner product on vectors. When I look at simply the vector space properties of the collection of all n by m matrices, hey, the vector space of all n by m matrices, real matrices say, is isomorphic as a vector space to R in M, n times m dimensional real space. Now, when I say matrix norm, there was that consistence principle that was added as an extra property. If I look at the collection of n by m matrices as a vector space, I don't worry about multiplying those matrices together. There's no matrix products of concern. But barring that, I can still talk about the first three properties in the definition of a matrix norm, and that's just the regular definition of norm like we had on a vector space. So the fact that, hey, when I take collection of matrices, their vector space properties are just exactly like the vector space properties of R n times m. So I'm not surprised that we can make a claim, since R n times m, all norms are equivalent, that all matrix norms are equivalent as well. Here's some specifics related to equivalence where they find particular parameters. Is there enough here? I don't think we can claim equivalence of any particular ones of these. Maybe we can show equivalence of a Frobenius norm and an infinity norm if I sandwich these top two together exactly right. Yeah, and maybe an L1 and an L2 norm we can show are equivalent, sandwiching these two together. But we've got a larger claim in that exercise up top. But these are specific constants that can be put on certain norms as compared to certain other norms. The norms mentioned here, the infinity norm, the L1 norm, the L2 norm, and the Frobenius norm. So proofs of those relationships is left as some exercise. It's back at exercise 2.30. Next claim relates matrix norms to the spectral radius. It seems like an odd thing to relate it to, but this, for any matrix A and a given norm, the spectral radius of A is less than or equal to the norm of A, is the claim. Remember, the spectral radius was, if you like, it's the modulus of the largest modulus eigenvalue of matrix A. I have to say modulus because when we talk eigenvalues, we might be dealing with complex eigenvalues. So this was the largest modulus eigenvalue of matrix A. Let's go through a proof of that. So we're relating eigenvalues to norms of matrices. Okay, there's the claim. Take C sub I, V sub I to be an eigenpair for matrix A. So in particular, we've chosen an arbitrary eigenpair, especially an arbitrary eigenvalue. We want to show this arbitrary eigenvalue of matrix A is in modulus less than or equal to the norm of A. since it's an arbitrary eigenvalue, that would establish the result for the spectral radius. Okay, consider the square matrix defined as follows. So we're going to take this eigenvector as the first column of matrix V, and then create a square matrix by filling in a bunch of column vectors of all zeros. So we're making the matrix V square. Matrix A was hypothesized to be square in this stuff. It'd have to be if we're talking eigenvalues. So V is the same size as A, and its first column is this eigenvector of matrix A, and everything, all the other entries are zeros. Then we claim matrix A times matrix V is C sub I times matrix V, and that could use some justification. Think of it like this. When I multiply matrix A times matrix V, what you effectively get is a matrix whose first column is matrix A times the first column of V. The second column on the right-hand side is matrix A times the second column of V. The third column on the right-hand side is matrix A times the third column of matrix V, and so forth. Well, look at the columns of vector V. I'm sorry, matrix V. It's that eigenvector followed by a bunch of zeros. So what do you get for the first column of A times matrix V? Well, it'll be A times that first column, A times that V sub I vector. So what we would get out from this product is A times V sub I for the first column. All the other columns in V, matrix V, are all zeros. A times those columns is all zeros. So what we're getting out from that matrix product is a matrix whose first column is A times V sub I. Hey, that's A times V sub I is C sub I times V sub I, because V sub I is an eigenvector associated with eigenvalue C sub I. So the first column is C sub I times V sub I, and all the other columns are zero. That's precisely eigenvalue C sub I times matrix V. First column, were I to take the C sub I inside the way we multiply, we'd get the C sub I times that first column vector and zeros everywhere else. So that's exactly what AV is. So there's an argument that that equality holds. So if we consider the modulus of C sub I, it might be complex, so I'm needing to use moduli instead of absolute values, times the norm of matrix V, the matrix norm, right? Any matrix norm. They're all equivalent, so we'll take advantage of that in some of our future manipulations, but for now, consider this norm. So if we take modulus of C sub I times the norm of vector V, we know that to equal the norm of C sub I times matrix V, definition of matrix norm. You brought scalars out by putting absolute value or modulus around them as appropriate, whether they're real or complex. C times V sub I, we just argued computationally, that's matrix A times matrix V. So we get a norm of AV just upon substituting. The consistency property of norms, of matrix norms, told us that the norm of the product is less than or equal to the product of the norms. So being a matrix norm has to satisfy that. All right, we're trying to compare, what was it? The size, the modulus, of the eigenvalues of A to the norm of A. Here's the norm of A. Here's an arbitrary eigenvalue, modulus of the size of an arbitrary eigenvalue. We just got this norm of V stuff in the way, and we can divide that out as long as that ain't zero. Hey, V sub I was an eigenvector of matrix A. By definition, eigenvectors are non-zero. So V sub I is a non-zero vector. So the first column of matrix V is not all zeros. And V is not the zero matrix, and the norm of V is not zero. So we can divide the norm of V out. That leaves us with modulus of C sub I is less than or equal to the matrix norm of A. C sub I was an arbitrary eigenvalue of matrix A, so all eigenvalues of A satisfy this inequality. The spectral radius of A was the modulus of the largest modulus eigenvalue, it was, I don't know, it was defined as a circle in the complex plane that contains all the eigenvalues. But equivalently, we can take it to be the eigenvalue, the modulus of the eigenvalue of largest modulus. Since the biggest modulus eigenvalue is less than or equal to the norm of A, then all the eigenvalues, which are contained in a circle in the complex plane of radius, rho of A, is less than or equal to the norm of A. Okay, so it gives us a relationship between, oddly enough, eigenvalues and norms. This was an arbitrary norm, a quick observation. If we take the A1 norm, that was where we summed over so we're summing over index I, so we're actually taking the sum of the jth column, absolute value, sum of the jth column of matrix A, and then taking a maximum of that. So this L1 norm was the maximum column sum. The L infinity norm here, we're letting the j's vary, so we're taking a sum over rows here and taking a maximum row sum. Well, we could use those norms up here and draw the conclusion that the spectral radius is less than or equal to both the largest sum of absolute values of the elements in any row or the elements in any column. Simply applying Theorem 3.9.6 to these particular norms and observing what they are, as we stated in the previous video 2-3 slides ago. All right, shifting gears, finally, if we've got a norm on matrices, then we can talk about the convergence of sequences, the convergence of series of matrices. So we can define limits of sequences of matrices and therefore of sums of matrices or series of matrices. The sum of a series is the limit of the sequence of partial sums. So if you can deal with sequences, you can deal with sums. All matrix norms are equivalent. So in doing this, we're going to assume just like a generic norm. The importance, we mentioned this when we talked about equivalence of vector norms. The importance of equivalence norms is they yield the same convergences. A sequence that converges with respect to one norm will converge also with respect to an equivalent norm. And same for divergence. A sequence that diverges with respect to one norm will diverge with respect to an equivalent norm. So that's why equivalence of norms is interesting. Not so much for the linear algebraic properties, but more for these analysis type things when we talk about limits. So for the remainder of this section, we'll just have primarily a generic norm. We could replace it with any known norm that's convenient, though, having these hold for all norms. So a sequence of matrices of the same size, A1, A2, A3, ... said to converge to matrix A if the exact same type definition you had when you talked about convergence of a sequence of numbers. For all epsilon greater than 0, there is a natural number n, capital N, such that when the index is greater than or equal to capital N, we have the distance from A to A sub n less than 0. We're measuring distance using the matrix norms. So we can make A sub n arbitrarily close to A, that is within epsilon, provided we make the index n sufficiently large. Capital N defines the sufficiently large. We can relate convergence to 0 to the spectral radius. As Theorem 3.9.7 says, let A be a square matrix, then the limit as k approaches infinity of a to the k power equals 0, meaning this up here, if and only if the spectral radius is less than 1. I'm thinking somewhere under this there must be some arguments involving geometric series. You're so used to taking a quantity less than 1, you raise that quantity to bigger and bigger powers, it gets closer and closer to 0. And that's exactly what we're doing. It's not that quantity, it's something else, but this must have something to do with the behavior of geometric terms. Let's look at a proof. Okay, so if and only if, first, let's suppose the limit as k approaches infinity of a to the k equals 0. That means an epsilon n thing. Let C1, V1 be an eigenpair of A, where C1 is a dominant eigenvalue of A. It was an eigenvalue of maximal modulus. So all other eigenvalues in size and modulus are less than or equal to the modulus of C1. It's convenient if we're having a conversation about spectral radius to talk about an eigenvalue of maximal size. Let epsilon be greater than 0. Well, we've assumed a limit exists, so that tells us there exists a natural number capital N such that for all values of the index, lowercase n greater than or equal to capital N, a sub k approaches 0. The norm of a sub k minus 0 is less than, let's take epsilon over the norm of v sub 1. I can put any, if I tell you up front what we're going to use, I can put any positive number I want here, and you can find the n. I choose epsilon over the norm of v sub 1 for reasons to be made apparent shortly. Hey, v sub 1, that's not the 0 vector, is it? No, it's an eigenvector, and the 0 vector is never an eigenvector. So we haven't divided by 0. All right, well, here's the reason we did that. Then for values of the index lowercase n sufficiently large, we have norm of a to the k v1 minus 0. That's just the norm of a to the k v1. So we can drop the 0 stuff, keep the norm stuff. This is less than or equal to the norm of the matrix, a to the k, times the norm of the vector. If you look at the way we define the induced norm, also maybe called the operator norm, that's more of an analysis setting, but the induced norm, where we took the norm of a matrix defined as the maximum of, matrix applied to a vector, norm of, divided by the norm of that vector to which it's applied, and divide by the norm of V1 and do some maximum or soup stuff is how the norm was defined. So the norm will definitely be greater than or equal to what we get out for any particular vector V1. So that actually comes from a definition. We had, let's see, we had a to the k power, norm of, less than epsilon over the norm of V1. So we can replace that norm with epsilon over the norm of V1. The norms of V1 cancel. We get epsilon. We just showed that for all epsilon greater than 0, there's a value of the index. There's a natural number, capital N, such that whenever the index lowercase n is at least that big, we get the norm of the difference less than epsilon. That's saying the limit of this matrix is that. The limit of this sequence of matrices is that matrix. The limit as k approaches infinity of a to the k v1 equals 0. That 0 matrix times vector, it's column vector technically. We have a to the k v1 equals c1 to the k v1 because we got into this mess by saying c1 v1 is an eigenpair. So a times vector v1 equals c1 times vector v1. I could use a reference here. We're actually applying this to a to the k power. Yeah, well, if we've got c1 v1 as an eigenpair of a, then we have c1 to the k v1 as an eigenpair of a to the k power. Result from the previous section when we were dealing with properties of eigenvalues. I think it was Theorem 3.8.2, Part 6. Just happened to have that sitting conveniently by. But that allows us to draw this conclusion. So we can replace the a to the k v1 with a c1 to the k v1 and get the limit as k approaches infinity of c1 to the k v1 equals 0. This is not a 0 vector. If you like, I could even bring that v1 vector outside of the limit. It's constant with respect to k. It was given up top somewhere. This we're stuck with. But this is just a sequence of numbers. So we have a limit as k approaches infinity of c1 to the k power. That must go to the 0 scalar. And the only time that happens is when we take a number of modulus less than 1. You certainly believe me if I say absolute value, and we've got real numbers. It holds for complex numbers as well. So we draw the conclusion that the modulus of C1 is less than 1. C1 was what? A dominant eigenvalue of matrix A. So it was an eigenvalue of maximum modulus. So the biggest modulus eigenvalue is less than 1. So the spectral radius is less than 1. All the eigenvalues must have modulus less than 1. And so the spectral radius must be less than 1. Okay, so that shows the limit of a to the k equals 0 implies the spectral radius is less than 1. It was if and only if we need to do the converse. So now suppose that the spectral radius of A is less than 1. Theorem 3.8.9 told us that a Schur factorization exists. Remember what a Schur factorization is? It means I can take matrix A and write it as an orthogonal matrix times a triangular matrix times the transpose or inverse of an orthogonal matrix. And we had the situation there where the T was, let's say it correctly, upper triangular, and T has the same eigenvalues of A. So all of that was a Schur factorization of matrix A. Suppose those eigenvalues of A are C1, C2 through C sub n. We'll need to refer to them specifically here shortly. All right. Fix some real scalar D, positive, and form an n by n diagonal matrix where the entries are D, D squared, D cubed, up through D to the n. Okay. No constraints on D other than it's non-negative, or sorry, it's positive. So we're making a diagonal matrix D as given. So here's what we've got. We got matrix A, we've got an orthogonal matrix Q and its inverse. T is upper triangular and has the same eigenvalues of A. By the way, that means being a triangular matrix, the diagonal entries of T must be C sub 1 through C sub n. That's how you how you find the eigenvalues of a triangular matrix or diagonal matrix. It's just the entries along the diagonal. And D is a diagonal matrix with those particular entries. All right, first thing we're going to talk about is D inverse. It's easy to find the inverse of a diagonal matrix. Just take the reciprocal of each of the diagonal elements. We're good. None of them are 0. If one of them is 0, then we're dealing with a diagonal matrix that's not invertible. But none of them are 0, and it's easy to find the inverse of diagonal matrix D. If we consider D, T, D inverse, okay, this is a diagonal matrix, this is a diagonal matrix, and T is an upper triangular matrix. Claim is we get an upper triangular matrix with the same diagonal entries as T. How about this? Product of two upper triangular matrices is upper triangular. It's a homework exercise back in probably around when we first encountered matrix products. So we've got a product of 3 upper triangular matrices. Diagonal matrices are also upper triangular. They're also lower triangular. But we got a product of 3 upper triangular matrices. So the product that results is upper triangular. How about the diagonal entries? Diagonal entries will result whenever we get products of the form, right? We're getting a matrix D has bunches of zeros and powers of D along the diagonal. So when we find diagonal entries of D times T, it's going to involve a power of D times a diagonal entry of T. When we take that matrix and multiply it by D inverse, then the diagonal entries are going to involve a power of D, a diagonal entry of T, and a corresponding negative power of D. For example, the 3, 3 entry of this matrix will be D cubed from the D matrix, D cubed, lowercase d cubed, times, I don't know, T sub 3, 3, times D to the negative 3. So if I look at the 3, 3 entry in the matrix product, it will involve a D cubed here, D to the negative 3 here, and a T sub 3, 3 there. Yeah, the reciprocal nature in which we've chosen the D's and the D inverses, we lose those. Diagonal entries are going to be the same as the entries of matrix T. The eigenvalues of a triangular matrix are the diagonal entries of that triangular matrix. We actually stated that just a few seconds ago. See example 3.1.a, the definition of eigenvalue, if you like. But yes, the eigenvalues of a triangular matrix are the diagonal entries. So the eigenvalues of this thing are the diagonal entries, which are the same as the diagonal entries of T. T's a triangular matrix, so the eigenvalues of T are those values as well. Hey, A has the same eigenvalues as the entries on the diagonal of matrix T because we used a sure factorization of matrix A. Let's check back on the previous page real quick. T is upper triangular. T has the same eigenvalues as A. And being upper triangular, those eigenvalues must be C1 through C sub n, and they appear along the diagonal of the triangular matrix T. Okay, so what we got out of that last claim, D, T, D inverse, T, and A, they all have the same eigenvalues. They're all C1 through C sub n. They're the diagonal entries of these two matrices. I don't know about matrix A. I know it has those as its eigenvalues. I doubt they're along the diagonal in matrix A, though. Okay, let's give these matrices, their entries, some labels. Call matrix T, capital T, the matrix with little t sub ij entries. D, little d sub ij's. I know a bunch of them are 0. D inverse, call them little d sub ij primes. I know a bunch of them are 0. And let's find the ij entry of D times T first. Well, I'll take the ik entry of D and the kj entry of T and sum up over K. Like I said, hey, D's a diagonal matrix. We're getting bunches and bunches of zeros. The only time the D sub ik is not 0 is when K equals I. When K equals I, we get D sub I. Here we get, I guess, D sub ij. We had to take K equals to I. So there's the only non-zero entry, and there's the sum. So if we want the ij entry of dt d inverse, okay, we're going to take that and multiply it on the right by d inverse. So that would be the ik entry of dt times the kj entry of d inverse. Let's do the easy one first. Kj entry of d inverse, yeah, d sub kj with a little prime on it. The ik entry of dt, well, here's the ij entry of dt. So the ik entry would be, change the j to a k. D sub ii, d sub ik. D sub ii, t sub ik. Definition of matrix product. Okay, again, we've got a bunch of zeros. We're getting them here now. The inverse of matrix D, D inverse, was a diagonal matrix, and it's got these powers, these negative powers of D along the diagonal. So we're getting 0, 0, 0, except when K equals J. When K equals J is the only time we'll get a non-zero entry out of all of these, so we can drop the summation and plug in K equals J. So the K here becomes a J there. The K here becomes a J. We get a D sub J, J prime. You know what that is? Yeah, that's D to the negative J. Look how the entries along the diagonal of D inverse are labeled. So we get a D to the negative J here. Similarly, D sub I, that was powers of D as well, positive powers. So we'll get a D to the positive I here. And we can simplify that a wee little bit as D to the I minus J times T sub ij. All right, so we just found the ij entry of this matrix product T, D, T inverse. Let's sum the absolute values of the jth column of D, T, D inverse. Okay, I've got the ij entries, so we can certainly do that. We'll fix the j and sum over the i's. So sum from I equals 1 to n. Whoops, why did we stop at j? It's upper triangular. So we'll get some non-zero entries. And remember, this was an upper triangular matrix. We said so right there. So we just sum from I equals 1 until we hit the diagonal. I equals 1 to j. The t sub I j's, we're interested in the jth column. We'll take the absolute value of this quantity. Hey, d was positive, so d to the I minus j is positive. So we don't need that in the absolute values, but I do need the t sub I j's in the absolute values. When we hit the diagonal, and I and j are the same, we get d to the 0, that's 1, d's positive. And t sub jj, that would be the jth diagonal entry in matrix T. Hey, matrix T has as its entries the eigenvalues of matrix A. So T sub jj will be C sub j, the jth eigenvalue of matrix A. We denoted the eigenvalues of matrix A as subscripted C's. That was just the notation in this proof. So we can peel off the I equals j term and get this C sub j, and here's the remainder of those terms. All right, remember where we're going on this. We're going for this limit equals 0. We've assumed the spectral radius was less than 1. Okay, so a few more computations on this. D was chosen to be positive. I minus j, that's less than 0 for I between 1 and j minus 1. I'm going to do the subtraction. You'll see that's definitely negative for those values of I. So when we consider d to the I minus j, if d gets large, we've got a large number raised to a negative power. The I and j being fixed and the d varying in this limit. This is just a claim about numbers. Right? There's no matrix stuff here. D is a number. I minus j is a number. That's the 0 number, scalar. So this is just a calculus 1 type claim. And as d approaches infinity, the d gets larger and larger. We're raising it to a negative power, so we're getting smaller and smaller numbers out, smaller and smaller positive numbers, and that'll give us certainly a limit of 0. So we're going to use an epsilon definition. Arguably, this is just calculus 1 stuff. Here, we'll take epsilon to be greater than 0. Then we know there exists an m, a real number such that whenever d is sufficiently large, greater than or equal to m, we've got d to the I minus j minus 0, absolute value of, that is absolute value. The distance between these two is small. I can drop the absolute values because I know the d is positive, this is positive, and this is what I want small to be. I want to take epsilon divided by j minus 1 times the maximum of the t sub I j's. Never mind why just yet. All right, and the t sub I j's, that was the entries in matrix T. So pick the one of maximum absolute value. We're dealing with real numbers on those, and use that in the denominator here. So the fact that the limit equals 0 says I can make that quantity as small as I want. I want to make it that small. J was fixed somewhere upstairs when we were talking about the jth column sum. So for given epsilon greater than 0, provided d is sufficiently large for this to hold, since the absolute value of C sub j, you have to think absolute value because it's a eigenvalue, and they could be complex. The absolute value of C sub j is less than or equal to the spectral radius of A. So if we look at some of the stuff we had on the previous slide, the absolute value, the modulus of C sub j plus the sum of the remaining entries, 1 through j minus 1, entries in the jth column of the matrix product. This quantity we had before, let's see, we know C sub j and modulus is less than or equal to the spectral radius. The strict inequality comes from the other part. We've got this d to the I minus j. We've got that thing bounded by this stuff here. So we'll replace the d to the I minus j with that stuff there. We get a t sub I j, absolute value of on the right-hand side, and that's why we chose the maximum thing. So what do we have here? we're summing from 1 to j minus 1. There's a j minus 1 down here. If we can make this constant, then we can do some canceling. So what we're going to do is say, hey, the absolute value of t sub ij divided by the maximum of the absolute value of the t sub ij's, that's less than or equal to 1. The numerator is smaller than this part of the denominator. Replace it with 1. I pick up an inequality. Now we've got the sum from 1 to j minus 1 of epsilon over j minus 1. There's no i's there, so it's epsilon divided by j minus 1 plus epsilon divided by j minus 1 plus j minus 1 times. The j minus 1's cancel to leave us with the spectral radius of A plus epsilon. All right, so we've got this quantity bounded above, strictly, I suppose, by spectral radius of A plus epsilon. Remember where we're going. I want to talk L1 norms. So in terms of the L1 norm, we had established some bounds in terms of arbitrary norms. So I want to use the L1 norm because it's a convenient thing to do this time. That was the column sum norm, as we called it in the previous video. We introduced the L1 norms and the L infinity norms. Let's use the L1 norm on dt d inverse. The L1 norm, that was the maximum of the column sums. Okay, we looked at the column sums of dt d inverse. That was 2 slides ago. We had this thing here. That's what we got for the column sum. Remember, we summed from 1 up to j minus 1. Then we added the diagonal entry, and beyond that, we were picking up zeros because we were dealing with an upper triangular matrix. So this is what we got for column sums. We take the maximum over all columns of this. That's what the L1 sum is, the maximum column sum, the column sum norm. And we just saw that this thing was bounded by the spectral radius of A plus epsilon independent of the j's, provided we had d sufficiently large and the moving variable may be scalar d. So we get the L1 norm here less than spectral radius of A plus epsilon. So we're going to use this to define a new norm. I'll refer to it as the D norm. We've got some things that hold for all norms, in particular the definition of limit of matrices, sequences of matrices. So we're going to define a norm, the D norm, for any n by n matrix X as the D norm is defined to be QD inverse inverse X QD inverse, L1 norm of. All right. First off, that really is a norm left as an exercise. So that thing really is a norm. Also, the Q and the D, they were determined upstairs. So we're taking those. We inherited the Q from, what was it, a Schur factorization of matrix A. And we inherited the D and the D inverse by having chosen some value for that positive parameter D. So we're taking Q and D from above, so they are fixed and determined, and defining apparently a norm, the D norm, say, in terms of the L1 norm. All right, really is a norm. Then, if we look at the D norm of matrix A, okay, that would be taking the X and replacing it with an A. So just place an A there. That's equivalent to, let's see, got an inverse of a product. That's the product of the inverses in the opposite order. That's how we get from here to here. We have Q inverse AQ. I believe that was matrix T. And here we've got then DT, D inverse. Do you believe Q inverse AQ equals T? Let's run back and check that. When we introduced the Schur factorization of A, that's exactly what we had. But let's run back and check that. So excuse me, I have to go back 3 slides. Here it is. A equals QT, Q inverse. Ain't that what I said? Well, the Q's were on the other side. It read Q inverse AQ equals T. Q inverse AQ equals T. Okay, so we got the substitution there. We've just shown that the D norm of A equals the L1 norm of DT D inverse. How y'all doing? We just found a bound, an upper bound, on the L1 norm of DT D inverse. Well, then we just found an upper bound on the D norm of A, because those are equal. Okay, here we've hypothesized that the spectral radius was less than 1. We're trying to show the limit of the sequence of the powers of matrix A is a zero matrix. It's really just an epsilon argument, but quite involved with all these matrices flying around. But we've hypothesized that the spectral radius of A is less than 1. So choose an epsilon and a corresponding capital M and a corresponding parameter D that we had up here, such that rho of A plus epsilon is still less than 1. There's a little bit of room between the spectral radius and 1. Pick epsilon so small that we have the spectral radius plus epsilon still less than 1. There's room because there's space between those two numbers. Pick epsilon sufficiently small for that to hold. Then we'll start using some of this equipment we got here. The D norm of A, we saw equals the 1 norm of DTD inverse. All right. We had the 1 norm of DTD inverse bounded by spectral radius of A plus epsilon. So we get that spectral radius of A plus epsilon here. We've got that less than 1. So we've got the D norm of A less than 1. If we take the D norm of A to the K power, so we're finally getting to the topic of conversation, the consistency property, norm of a product is less than or equal to the product of the norms, a property of matrix norms, the consistency property, apply it K times. The norm of A to the K is less than or equal to the norm of A to the K. In this case, we're using the D norm, but it holds for all matrix norms. This really is a norm. Details to be supplied later. Right? Since we just argued the D norm of A is less than 1, when we take the D norm of A, raise it to power K, let K get large, we're going to get out 0. The D norm of A, it's some number between 0 and 1, and strictly less than 1. Raise it to higher powers, it gets closer to 0, it has a limit of 0. We've got the comparison here that the D norm of A to the K is less than or equal to the D norm of A to the K. So we can, property of limits of real numbers, compare the limits correspondingly, take a limit as K approaches infinity on the left and the right. And I know what happens on the right, that goes to 0 because of this property here. So the limit as K approaches infinity of A to the K must equal 0. We've got the norm going to 0. So with respect to, as I was to say, with respect to matrix norms, since all matrix norms are equivalent, we can draw the general conclusion. But we've got the norm going to 0, so the matrix must go to 0 as well. The limit as K approaches 0 of A to the K must equal 0. And that was the converse. Okay, so back to the notes. We're actually going to use this for something somewhat more interesting, but we've got that property in terms of the behaviors of powers of matrices, relating or applying when the spectral radius is less than 1. Turns out, for any matrix, you can actually express the spectral radius in terms of limits of norms. Claim in the next theorem is, for square matrix A, we wouldn't be having any of these conversations unless they were square matrices. We're talking spectral radius, so we're talking eigenvalues, and those only work for square matrices. So for square matrix X, we're claiming that the spectral radius of A can be determined by computing the limit as K approaches infinity, the norm of A to the K, K through of, the norm of A to the K, 1 over K. No restrictions on the norm. all norms are equivalent. So as I said, we're doing some of this stuff with a generic norm. So any matrix norm, this property is satisfied. Let's go through a proof of that. Okay, this isn't nearly as lengthy as the previous one, maybe a couple of slides. All right, two results back. We showed the spectral radius was less than or equal to the norm of the matrix. Any matrix norm satisfies that property. Left as an exercise, because it's in the previous section. The spectral radius of a to the k is the spectral radius of a to the k power. A little property on the eigenvalues of a matrix and its powers is how that's shown. But we'll take that as given from an exercise. So if we look at the spectral radius of a to the k power, that's the same as the spectral radius of a to the k power. I can have the exponent outside the radius or on the matrix. And we just saw spectral radius of a matrix is less than or equal to the norm of that matrix. Let's apply that result to the matrix a to the k. So the spectral radius of a to the k is less than or equal to the norm of a to the k. Look at this equation, take the kth root of both sides. So the spectral radius of A itself is less than or equal to this, to the 1 over k power. Raise both sides to the 1 over k power. That's an increasing function. It preserves the inequality. So we get the spectral radius of A is less than or equal to the norm of A to the k power, 1 over k. So we're close. We want to show limit. We want to show the limit of this quantity on the right actually equals the quantity on the left. So start equation, we'll be referring back to that upper bound on the spectral radius here in a little while. All right, theorem 3.8.2 part 2 said if C is an eigenvalue of matrix A, then for any scalar B, including complex scalars, BC is an eigenvalue of the matrix B times A. So the spectral radius of B times A equals B times the spectral radius of A. Any eigenvalue of A produces an eigenvalue of B times A of the form multiple of that eigenvalue of A, multiple of C, and conversely. So we can draw a conclusion about the spectral radius. The argument up here is fairly similar, it turns out. So let epsilon be greater than 0. Consider this matrix. 1 over the spectral radius of A plus epsilon times matrix A. Okay, well, we'll take that thing there as a scalar, like we were just talking in terms of this relationship between spectral radii. And we'll say the spectral radius of this multiple of A equals that multiple of the spectral radius of A. So B is playing the role of 1 over rho of A plus epsilon. We get a 1 over rho of A plus epsilon times rho of A on the right-hand side. So simplifying a wee bit, we get that the spectral radius of this matrix equals this quotient. This is strictly less than 1. Epsilon's greater than 0. The denominator is bigger than the numerator, so the quotient's less than 1. I like quotients less than 1 in a conversation about convergence. If I raise that to powers, it's going to get little. So if we take a limit as k approaches infinity of 1 over the spectral radius of A plus epsilon times matrix A to the k power, that'll go to 0 by theorem 3.9.7 because its spectral radius is less than 1. This matrix, we just said, has a spectral radius less than 1. Spectral radius is less than 1, then the limit of the powers of that matrix go to 0. That thing we just did. That's the, I think that was the first half. I don't know, we had if and only if, so we're only using half of theorem 3.9.7. We're using the half that says if the spectral radius of a matrix is less than 1, then that matrix, when raised to powers, has a limit of 0. So, were we to raise this matrix to powers, the scalar out front just picks up an exponent of k. Matrix A picks up an exponent of k. We must have, if you like, the norm of this matrix minus the limit value. But same thing, the limit value is 0, so we're just looking at the norm of the matrix. And we can say then the limit of the norm of that matrix, which can be expressed like this. All we did was take the scalar multiple out of the norm, put an absolute value on it. It doesn't need one. These are all positive numbers. So we get this as a scalar out front. That limit must be 0. Hey, the only time a matrix has a limit of 0 is when its norm has a limit of 0. It's a little comment at the bottom. So we've got a limit here that goes to 0. Rho of A plus epsilon, is that still in front of us? That was chosen in such a way that that was less than 1, by the way. Okay, so definition of limit, dealing with, let me go back and pick it up again, dealing with this limit, the fact that that limit is 0. By the way, that's a limit of real numbers. So this is really just calculus 1 stuff, maybe calculus 2. It's a sequences of real numbers. K was a natural number, right? It's an exponent on matrix A. Limit of sequences. So limit of sequences of real numbers is the good news. The numerator is a norm, so it's a real number. Denominator's a real number. So let's take an epsilon definition of a limit of a sequence of real numbers being 0. And that gives us then that there's an m, a real number, such that when the k parameter is sufficiently large, the capital M is sufficiently large, then we can make that quotient of real numbers less than 1. We can actually make it really small, but we can make it less than 1 in particular. And by having that inequality cross multiply, get the rho of A plus epsilon to the k power on the right-hand side, take kth roots, also an increasing function, preserving the inequality. We get A to the k, norm of 1 over k is less than spectral radius plus epsilon, provided k is sufficiently large. Okay, remember before we had the spectral radius of A less than or equal to this quantity, which is what we originally had. Now we've got this quantity bounded above by spectral radius plus epsilon, provided k is sufficiently large. So what happens when I take a limit? We've got the, well, excuse me, let me say, for any k sufficiently large, we have these as static upper and lower bounds. I'm looking at the wrong thing to change. It's this I want to change. This is true for any epsilon greater than 0. So I can take this epsilon as small as I want to, and that's going to squeeze down this thing being sandwiched between rho of A and rho of A plus a little bit. This must equal rho of A. This was done for arbitrary epsilon. We must have that we get this for k sufficiently large, it's where the limit comes in, equals rho of A. Sort of a sandwich type thing, not exactly a sandwich theorem, but a comparison, and then taking of a limit. So we get the limit of A to the k, norm of 1 over k to equal the spectral radius. There's the spectral radius expressed in terms of limits of norms of powers of the matrix for what it's worth. Well, here's what it's worth. All right, so many of these results are just, look at this relationship. Well, theorem 3.9.9, look at this relationship. This one looks familiar. A is a square matrix with norm less than 1. Claim is I plus, it's the first time we dealt, and possibly the last time, we dealt with a series of matrices. The limit as k approaches infinity of sum from n equals 1 to k of A sub n. So what we've got on the left-hand side, it's really a power series. I would like to interpret A to the 0 as the identity matrix. Then we've got A to the 0 plus A to the 1 plus A squared plus A cubed, dot, dot, dot. So we've got a series. We've got a series. I would like to write it from n equals 0 to infinity, A to the n. If by A to the 0, I mean this thing over here. I mean the identity. Dude, that's a geometric series. its powers of A. What do you think a geometric series would converge to? Well, I take sum from n equals 0 to infinity of r for ratio maybe. I get 1 over 1 minus r. That's how geometric series behave. Hey, look what we're getting. We're getting, forgive me, 1 over 1 minus a. Same thing. This is exactly like a geometric series. And the proof will be quite similar to the way you show a geometric series can be summed to give 1 over 1 minus the ratio. So this is behaving exactly like geometric series. We've even got the condition that r has to be less than 1. Well, okay, the norm of matrix A has to be less than 1. So this does look familiar if I couch it in the right language. I can't say reciprocals, right? I got to have multiplicative inverses. So we've got an assumption also that we must have invertibility of this matrix. Let's go through and look at a proof of that one. It's just so analysis 1, maybe calculus 2. It's just so like real numbers. All right, good news. It's only one little slide. So let's introduce a sequence of partial sums. What we're getting over here, we've got, I say when k is 0, if you like, we've just got the identity. When k equals 1, we get the identity plus a to the first power. When k is 2, we get the identity plus a to the first and the second power, and so forth. The kth partial sum would be, this is exactly what's written here without the limit stuff. All right, we can take this representation of the kth partial sum, multiply it by I minus a. Might want to convince yourself there's a lot of cancellation that happens when you do that. You're left with I times the first term minus a times the last term. The last term is a to the k, so that'd give us a minus a to the k plus 1. All the intermediate things cancel. It's like a telescoping sequence. It telescopes. You get loads of cancellation, except for the first term and the last term. The minus introduces lots of cancellation. So we get I minus matrix A times this kth partial sum can be expressed like this. We've hypothesized the norm of A is less than 1. So a to the k approaches 0. The 0 matrix, powers of matrix K approach 0. If you like, take a to the k minus 0. That would be the norm of a to the k. Just drop the 0. What happens with this? Consistency property allows us to take the norm of the product is less than or equal to the product of the norms. It's consistency property and some induction if you want all the details. And we've got this norm of a to the k power. What happens when k gets big? Well, norm of a is less than 1. You take a number less than 1, a non-negative number less than 1, raise it to powers, it goes to 0. So it must be this goes to 0, and matrix A sub k must approach the 0 matrix. That was a cheap version of an epsilon proof. So when we take the limit of I minus a times s sub k, that's the same as the limit of I minus a to the k plus 1. Those things are equal, as observed above, that telescoping property. You can bring the I minus a outside. It doesn't have any k's in it, constant with respect to the limit. We get I minus a times the limit of the s sub k's. Over here, take a limit of a sum, that is the constant, the identity matrix, bring that negative outside. We get a limit as k approaches infinity of a to the k plus 1. We just saw that this, we expressed it with an exponent of k instead of k plus 1, but the limit's still the same. This goes to the 0 matrix, and we get the identity out on the right-hand side. So here's what we've got. We've got I minus 1 times something equals the identity. These are square matrices, right? Square matrices. So I don't have to check the product in the opposite order for square matrices. This must be the inverse of I minus 1. That is, I minus 1 inverse must be the limit of those partial sums. This thing here is the limit of those partial sums. It's just written in terms of limit notation. And that was the claim. So we get matrices of norm less than 1 to behave when we raise them to powers, dude, just like real numbers do, just like complex numbers do as well, in this geometric series way. Okay, a little bit more on the notes. A square matrix such that when we raise it to the k power and get the 0 matrix out, but we didn't get the 0 matrix out for 1 less on the power, is called a nilpotent matrix of index k. So k is the smallest exponent you can put on the matrix to get 0 out, if such a thing can be done. Last claim relates to nilpotent matrices of order k. It's just a little add-on topic here. Suppose A is n by n, which is nilpotent of order k. Claim is the spectral radius of A is 0. Well, now that's a bound on the largest eigenvalues of that matrix. If the largest one's size 0, they're all size 0. All eigenvalues in matrix A must be 0, in other words. The trace of A must be 0, another implication, and the rank of A must be less than or equal to n minus 1. It's not full rank. That's what the third part says. Proof of this is to be given as an exercise, and there's our exposure to norms of matrices and using them to talk about limits of sequences. That a to the k thing went to 0 there, and an application to series. This is actually an infinite geometric series that we've got here. Can't talk sequences in series unless you can measure distance. We measure distance with norms, we're good to go. So we can do, with our matrix norms, sequences and series of matrices. And that takes care of section 3.9, the vast majority of chapter 3, the bulk of the course. Whenever you're watching this, may or may not have a video for section 3.10. It's a quick little section, and I'm not sure we got time to cover it anyhow. But I'll see you in the next chapter. Likely, if you're taking the class, this is probably we're going to chapter 5 to try to get a little more properties of matrices. The stuff in chapter 4 is less important. I'll try to get videos out for that as well. But hopefully, I'll see you in chapter 5 soon. Have a nice day.